Hello and welcome. In this video, we're going to take a look at some rules that limits obey. They're called the limit laws. And what they're going to do is be able to help us to be able to calculate the value of a limit without actually needing to draw the graph of it. Just by having the function in front of us, we'll be able to see if we can calculate the limit as x approaches a of that function. So let's start off with a couple really basic types of limits. These two basics here. The limit as x approaches a of c equals c, where c is a constant. Now hopefully this should make sense, because if we have a function f of x equals c, then it's just a horizontal line. So here's a graph of y equals c, and imagine that we're trying to find the limit as x approaches some value here a. And as x is approaching a, picking a point on this line on either side and approaching a, it appears that our y values, since they're always the same, are going to remain constant and remain at a value of c. So it makes sense that the limit of c as x approaches a is simply c. Now, in this other case here, the limit of the function x as x approaches a. Well, we can try to imagine what the graph of y equals x looks like. Well, here is the graph of y equals x, and here is some value a. We wish to approach a from the left and from the right, and we do know that there's actually a point on the graph here at the coordinates a comma a. Now if we start at a point slightly to the left or slightly to the right, and we start approaching a, we're going to see that our y value approaches a from the left and approaches a from the right. So it kind of makes sense that the limit of the function x as x approaches a is simply equal to a. And let's basically start there. That is going to be the first couple limits that we can truly evaluate without needing a graph anymore. Just if we have a constant, then taking the limit as x approaches a is still going to be that same constant. That's the whole idea of it being a constant. And having a function x, if we let x approach a, well, it kind of makes sense that that is going to approach the value a. Starting there, then we can attack a whole lot of other limits using a series of other limit laws. Now let's suppose that f of x and g of x are any functions, but when we take the limit as x approaches a, let's suppose that at least the limit does exist. Let's suppose that the limit of f of x as x approaches a is L1, L for limit, 1 for just being the first equation. And then let's suppose that the limit of the function g of x as x approaches a is some other value. We'll call it L2. Okay, well, if you wanted to take a look at the first rule here, this is really just addition. If we take two functions, f and g, and we add them together, then when we take the limit as x approaches a of the sum of the functions, then, well, we can actually just figure out individual pieces. What is the limit of f as x approaches a? What is the limit of g as x approaches a? And add those two values together. So in this case, we get L1 plus L2. And the second rule is just going to be for subtraction. Second rule, if we have a difference of functions, take the limit of each individual function, subtract, and get, in this case, L1 minus L2. Now, using c as a constant here again, c is any constant multiple of a function f. If you take a function and you multiply it by c, it's essentially just going to be vertically stretching or shrinking it, which is going to change the y values accordingly. Now, looking at a limit as x approaches a, we can just go and take the function not multiplied, not scaled by c, take the limit as x approaches a, find out what that value is, which apparently we know is L1, and then we'll just scale that by c. So a constant, or a constant of a function inside a limit, can then just be removed, placed out front, and we can take the limit of the function and then scale it by c afterwards. Kind of a handy rule there. And this would be referred to as a constant multiple rule. The fourth one and fifth one, we can see they have multiplication and division, and they work very much the same way. If we ever have multiplication or division of functions, then we'll take the individual limits of each individual function, and then we'll multiply or divide those. Just keep in mind that when we are looking at division, the final result, L1 over L2, is only defined so long as this value in the bottom, the limit of g of x as x approaches a, is non-zero. It is quite possible to divide functions and both limits exist, but as a result, we end up divided by 0. We'll have to tackle those a little differently. Now, 6 and 7 are very much related. In number 6 here, it's essentially an extension of multiplication of multiple functions. In this case, we just have a power of f. If we have any sort of power of a function whose limit exists, take the limit of the function, take the result, and raise it to the power, which is great. Now, what if that power happens to be some sort of fraction? Fractional exponents can be translated into roots. And so question, or rule number 7, is very much the same. It's just instead of an nth power, we have an nth root. And if we have the limit of the nth root of some function, whose limit does exist, then apply the limit concept to the function, and then take the nth root of it. Now, of course, a little note here is if we have a square root or a fourth root or any even-powered root, this is not going to be defined if we're trying to take the root of some negative value. So we'll have to assume that in this case, L1 is greater than or equal to 0 if n is even. Okay, so with all of these rules, plus the two basic ones at the top here, now we can start just applying the limit piece by piece across all of these different operations. We've essentially covered all of the algebraic operations: addition, subtraction, multiplication, division, and powers. So let's put this all together and just do one example here of evaluating a limit of some function with a combination of algebraic operations. Okay, so I've got a rational expression that's a polynomial divided by a polynomial, and we've got 3x squared plus 2 over 2x minus 1. Now let's see what happens as x gets closer to 2 from a left-hand perspective or right-hand perspective, just getting closer to 2. Well, the first thing is, assuming that the top has a limit that exists and the bottom has a limit that exists, then we can split this up into a limit of the top and a limit of the bottom, and then divide those two results. Now you might want to think about which of the rules I just used. This is division, and that's rule number 5. And rule number 5 only works as long as the limit that I'm looking at in the bottom here doesn't end up equaling 0. So you might want to take a little note here that this is only going to be accurate so far, assuming that this limit in the denominator is non-zero. If I go through a few more steps here and I find out that I have 0 in the denominator, then this will all have been for nothing. But we're going to carry on and see what happens with the addition and subtraction of terms in the numerator and the denominator. So looking at the numerator, I've got two terms added together, and I'm going to use another limit rule here and take the limit of each individual term and then add the two limit results together. Okay, well now this is starting to look like many smaller limit problems all put together. You might want to think about what rules I've just applied there. I've used the addition and subtraction or difference properties, and that would be rule number 1 and rule number 2. And there's no restrictions, so long as the limits exist for all 4 limits, then so far we're on the right track. Now, you can see that we do have a couple constants already, 2 and 1, so those would be like our constant basic rule. Anytime that you're trying to take the limit of a constant as x approaches anything, you're going to be left with just the constant. So those are the first two limits that we knew already would exist once we get down to a constant. But the other two limits, 3x squared and 2x, have more pieces that we can start to simplify. So let's first start off with saying, well, this is 2, and on the bottom, this is 1. And those two limits we can evaluate because they are so basic. But let's take a look at this constant multiple rule, take a 3 out, and look at the limit as x approaches 2 of x squared. And on the bottom, constant multiple of 2 can be pulled from the limit, and we can look at the limit as x approaches 2. And again, that's another one of our very nice basic rules there. The limit of x as x approaches a number is simply going to be that number. So we know that that limit exists as well. And in the denominator, this is going to be becoming 2 times 2 minus 1. And we can go back to this condition that the limit in the denominator must be non-zero. And we can see that that is totally fine because we're going to end up with 3. How about the numerator? We're not quite done. We haven't actually looked at the limit of x squared yet, but it does have a power. So we can go and use one more rule here. We're going to take the limit as x approaches 2 of just x, and all of that will end up being squared. And finally, since that's another one of our basic rules, we know that that value is simply 2. And there we go. We've got rid of all of the limits, and we've evaluated each of them using various different limit laws, plus a couple of our really basic cases. And now we can compute what that value is. And we are left with 14 over 3. So we've got the value of this limit now. Now, of course, you may have noticed that if we were just to have defined a function, f of x equals 3x squared plus 2 over 2x minus 1, then f of 2 produces exactly the same result of 14 over 3. So why did we have to use limits after all that if we could simply have plugged in a 2? Well, good news is we can turn that into a theorem. Now this theorem applies to polynomials or rational expressions like we just looked at here. And if a is in the domain of f, then taking the limit as x approaches a of the function is simply equal to f of a. That would just be direct substitution. So you have the option of just plugging in a so long as you have a polynomial or a rational expression and that function is defined for a. Now oftentimes, and this comes up when we're looking at the tangent line problem, oftentimes we are trying to take the limit of some variable as it approaches a value where the function is not defined. And then we might need another theorem that allows us to circumvent that problem. Now, this theorem works by taking a function f and a function g that are almost identical. The only difference between these two functions is perhaps at the value x equals a. The two functions are exactly the same, except that we may have one function, let's say, is not defined at a, and the other one is defined at a. Now, if you have that kind of circumstance, then the limit as x approaches a of f and g are the same. Let's see if we can take a look at an example where this would be a useful theorem. Okay, in this example, we've got another rational expression. There's a polynomial divided by another polynomial. We're taking the limit as x approaches 3. Now, if you try to just use the direct substitution principle here and try plugging 3 directly in, you're going to find out that you're dividing by 0. And so you won't be able to use that principle. You'll have to do a little bit of preliminary algebra first and see if you can somehow take this function, x squared minus 9 over x minus 3, and get it into an equivalent function that's exactly the same, except perhaps at x equals 3. So while you're doing the preliminary algebra, make sure that you're leaving this limit operation to the very last step. You're going to have to keep writing this down, or of course you maybe want to do some work off to the side and come back to the limit. But you can continue to write this limit, showing that that's your final operation, and in the meantime, start factoring your difference of squares. Now, once you've factored it, it's still exactly the same function with exactly the same problem that x cannot equal 3. But canceling a common factor, and you're left with an equivalent function. Once we've canceled the x minus 3, an equivalent function is simply x plus 3. The only difference between x plus 3 and x squared minus 9 over x minus 3, we might say that those two are equal, except that in this one function on the right-hand side, x cannot equal 3. And in the right-hand side, well, if you plug in 3, it just ends up equaling 6. So these two functions evaluate differently when x equals 3, but that's okay. They are identical for every other value. And using this theorem, now that we've got the limit of x plus 3 as x equals c, if that limit exists, and it does, it equals 6 by using direct substitution, then we know that the original function, x squared minus 9 over x minus 3, will also have a limit as x approaches 3 equal to 6. So that's how that limit's going to help us get around problems where we can't use direct substitution. Now, this idea of some manipulation and that preliminary algebra is going to bring back a lot of algebraic skills that you may not have used for a while, but certainly factoring is a big one. You may also have to use a little bit of rationalizing to try to simplify. It really depends on what kind of function you're left with. But we are going to see several examples of this in class. So be prepared to get ready with some algebra skills, and then we can evaluate limits. Thanks for watching, and I'll see you in the next video.